All right. Thanks, everybody. Thank you to all the committee members, to everyone present. So today I'm going to talk about my thesis proposal topic, which is advancing spacecraft autonomy, optimal GNC, vision-based estimation, and systems integration for small spacecraft. Okay. So there's a current trend in the aerospace industry of downsizing of spacecraft. So let's look at an example of imaging spacecraft. You can say like stuff, usually the traditional way of doing things was huge spacecraft, the size of a bus, the size of a car, of a fridge. And there's been this trend of downsizing all the way down to stuff like this that can fit on your palm of your hand. And essentially the way things were done in the past is like everything was custom made, everything was, billion-dollar projects that would last years, and everything would be super hard and complicated, would involve a huge amount of people to work with. But there's now this trend of very few satellites turning into a lot of small satellites that, although they don't live as much, you have a huge number of them that can operate for shorter periods of time, but then that brings some things in consideration. So, and that makes a huge impact in the world. For example, this is from Planet Labs. They were tracking a wildfire in California, and it helped a lot with the teams that were localizing the fires and try to extinguish them. And also there are other applications, for example, with agriculture. So you can track how your crops are being grown, what's the productivity of each area and landmass, and can help farmers produce as much from their land as they can. And all of that has been enabled through the use of small satellites. Now, there's a few things. So satellites have been getting really small. So they've gotten 80 to the size of a quarter with a Zach per scale. So if you're launching like hundreds of small satellites, it's unreasonable to expect that people on the ground are going to be able to operate each and every one of them. So, but more dumb satellites also requires more bandwidth for ground stations. So for example, that huge antenna to the left there is the DSN. And as it's used for a bunch of deep space missions and a lot of large missions, it has a lot of demand, which has been currently being supplemented with sometimes, like for other missions, smaller missions, with homegrown, homebrewed ground stations. But that's the thing. We have now robots. There's a bunch of cool things happening with autonomy and a lot of new developments in embedded systems that enable things to be a lot smarter. So for example, GPUs, embedded GPUs, new cameras, and especially TinyML and a lot of very resource-constrained machine learning. And those things could actually be the key to enabling things like that to happen on spacecraft. Now, let's say compared to terrestrial robots, for example, this is a quadruped from Boston Dynamics that had a gas power generator in it. And as if we try to put it in space, it wouldn't be that great of an idea. And sometimes, excuse me, those robots on Earth, if they break, you can repair them. It's something you cannot do in space, that you can get a lot more energy. So there's a lot of constraints in space. They're kind of different from the constraints you're going to see in terrestrial robots. Now, the big research question here emerges then, how to enable these high-level tests for small resource-constrained spacecraft. And here I'm going to list a few of the problems that I'm going to tackle with my contributions. So there's under actuation and low control authorities. So you cannot fit a bunch of controls into a small spacecraft, how we deal with that. Lack of resource-only navigation. So how can you enable things on board to do navigation? Barrier to entry for hardware, software, the things we were talking about earlier, like how can we make systems that are not custom and easily accessible so that researchers and educational institutions can get access to them. And then also, at the same time, kind of like adjacent to the onboard navigation, there's a reliance on ground infrastructure for a lot of the tasks that are assigned to spacecraft. So how can we actually get to do that thing in space? So, and here my contributions for those areas include resource constraint control for small spacecraft, published in Sparrow this year. Then visual-inertial navigation, published last year in ICRA, under submission now for Space Computing Conference. Then there's been open source hardware published in small set this year. Then there's reliance on ground infrastructure, which is the proposed work. which is onboard georectification. So this is a list of publications that are submitted, and now let's focus a little bit on under actuation and load control authority, which are these three related here with by formation, Prometheus, and the magnetorquer controllers. So let's start with reaction wheels being unsuitable for small satellites. So if you look at reaction wheels, those are big wheels that spin, and you can use that as Newton's first law. You spin the wheel, you spin the spacecraft back. With the space station, if you look at the mass of their reaction wheels compared to the mass of the spacecraft, it's super tiny. Now, as the size of the spacecraft gets smaller, those actuators get a larger proportion of the mass that you're sending up, and that's a big constraint on what you can do with the rest of that mass. So then in that context, magnetorquers are awesome for that. You can just fit them inside a PCB, so a printed circuit board, and you can just use the magnetic field of the Earth, some wires and some current, and with some clever ideas, you can use that to create torque. Now, those things, they have somewhat of bad limitations. So you cannot create any torque in the direction of the magnetic field for the cross product nature of the torque that you're creating. And also it's very weak compared to reaction wheels. Now, one such condition where applying that is perfect is sun pointing, because you can only spin this, the spacecraft can still spin while doing the pointing. So you really only need 2 degrees of freedom for rotating instead of 3 for applying your torques. Now, one way that we can achieve that is through spin stabilization and then axis pointing in a sequential manner. So first, let's say a satellite's tumbling at a random rate. Now just spinning around in space. You want to spin it through one of its principal axes of inertia to ensure a stable spin, and then slowly nudge that angular momentum to whatever inertial reference that you're looking at. But how can we guarantee that? So we want to make sure that this is something with mathematical guarantees, because for small spacecraft, there is not a lot of a resource in terms of energy. So pointing your solar panels to the sun is of utmost importance. And Lyapunov-based controllers are awesome for giving this sort of stability guarantee. So you just pick one function, v of x, that's always larger than 0. And then you got to ensure that the v dot, the derivative of that, is always less than 0. So it's a function sort of shaped like this bowl, and you're following this trajectory going down the bowl. And by ensuring that you're always going down this bowl, your system will be stable. Now, there are a few important things here to notice. Here, dx dt is a function of x and u while you're doing the chain rule over v dot, but that is your dynamics. And this is how we can use and leverage that to use our controls to make a stable control for our system. And for one such example, you can choose that to be wherever you want, but one such example would be to minimize v dot and then find whatever control input that minimizes that. So you're making sure you're always going as fast as you can down that bowl. It's one of the possible ways to do it. There are many others. It's just an example. Now, let's start with the 2 of the tests separately and go look first at pointing your satellite at one of the principal axes of inertia. So let's call that axis A. So just okay, let's just evaluate how far we are from that axis of inertia, just looking at the difference of the norm of the difference between age and A, age being your angular momentum and A, that inertial reference, the principal axis of inertia. Then, as the same we were showing before, take the chain rule, use your dynamics for that. But then here, the critical part is your dynamics is the cross product from Euler dynamics and rigid body dynamics is just minus b, which is the magnetic field of the Earth, cross your control input. And from there, using the v dot, doing some math, you can figure out that, well, cool, I can use this control input to ensure that v dot is always negative. And one such example would be just make that quadratic. You have a negative sign in front of it. So perfect, you're always negative. And this is some research that has been done by Zach in the past. You show you can do with something that's called a flat spin recovery. So you switch between the principal axis of inertia, and this is a trajectory of angular momentum over time. So it just shows it's spinning from one of the principal axes into the other one that's marked with a green star. Now, spin axis pointing relies on stability of spin stabilization. So now that we've come from, cool, we have our satellite spinning in one of the principal axes of inertia, we want to nudge that all the way to the sun. So just grab one of those inertially fixed ones, and the same ideas that we showed before. So we grab the norm of this difference, which is a blue vector. And then there's a subtlety here, by the way, to notice that this inertially fixed vector is in world frame, while previously it's in body frame. You just need to make sure that in that case, for something that's measurable on the spacecraft, that you're doing this transformation constantly. So then you get a very similar flavor of control input, same thing, B cross this difference vector. You're just using that to normalize. I forgot to mention that earlier, gamma is just some factor to normalize age, so you can ensure that age has a certain magnitude as well. And as I said before, this is exactly the same. But how can we combine both tasks in a single function? So one of the ways we can do that is let's just naively combine them in a linear fashion. So just add them both together. Now, that doesn't really work when you do the chain rule and do all the same things that we've done in the past previously with v dot. You get some control input that's dependent on both the solar vector and the principal axis of inertia. So you just end up pointing to some random vector that's in between those two, which is not truly representative of what you're trying to do. So much so that this is bad. And this is what happens. You get like some failure cases, for example, right here, towards the end on the sails. There are some cases where it just doesn't work because it's not exactly what you're trying to do. So how do we fix that? We can let's look at first at the two separate functions, V1 and V2. So one of them for spin stabilization, one for spin axis targeting. They're just two bowls with somewhat different shapes. Now what if we just grab the maximum between the two of them? So then we say, okay, if I'm doing worse in spin stabilization than in sun pointing, I can just make sure that I'm always spin stabilized and then do sun pointing. Or if I'm already sun pointing and I've gotten unstable, I can go back to that. Cool. That would work pretty well, right? Just a logic system, pretty nice, but this is not differentiable. So how can we do this in a way to prove that this is actually something cool that will work? Now, how about we use an alternative, which is this softmax, which is a log's sum of exponentials. So here, just grabbing this max function, which is just like a straight sharp edge corner, and you're turning that into a smooth function, which produces a very similar result. And that's something we can use to differentiate. And now that we've got that, we can differentiate through that, do the same stuff with chain rules and using the things with dynamics. And now you got something which is a soft argmax. And in this way, all of the nice things about using that maximum logic can be differentiable, and therefore you can do Lyapunov's proofs of stability. And then you can just, if you just take an edge case, if you take off the smoothing factor and just, in an infinite case, it turns into a max, you can just go, okay, I can do the maximum of the two and then do the same nice maximum of the two functions that we were looking at before. And then because we're doing that with magnetorquers, you can just saturate your magnetorquer in that direction to ensure that you're creating always a control input that is doable by your magnetorquers. And here's a plot of the angular momentum of an angular momentum trajectory, and it's color coded for spin stabilization. It's an axis pointing, and it's really interesting here to see how it alternates along the trajectory between spin stabilizing and nudging the angular momentum vector. And we've done a few numerical simulations to show the stability guarantees of a 550 kilometer sun sync orbit, just with a goal of 10 degrees per second of angular velocity. And we use a flight mission characteristic for that. You can see like all of them always converging nicely towards the end of that tail. And here, compared to the naive linear combination, you can see that to the left, there are some cases where, you got like 20-ish something degrees of failure, and it's all like super squiggly. And the Lyapunov controller with the dual with the maximum function is always super stable and nice towards with that tail. And then we repeated the same thing to show that on the LEO case also that would happen in a 440-kilometer LEO orbit. One thing here is also that a lot of times those controllers rely on a change of the magnetic field of the Earth. So in this case of a LEO, there's less change in direction for the magnetic field, so there's a little bit less control authority. And then it gets even more pronounced compared to the baseline that even though there are sometimes it takes a little bit longer, the Lyapunov controller to the right always gets the job done, while the baseline has a few failure cases. And a really cool thing that happened with this research was doing an orbit demo with Pi4. So those were 4 1.5 U CubeSats that were launched in collaboration between CMU and NASA Ames, launched February last year. It uses Pi-cube avionics framework. We'll go in a little bit more detail to that later. It's a similar thing to the simulations, 550 sun-sync orbit, and you had as its main purpose to demonstrate small-scale GNC and other relative ranging techniques and a bunch of those flavors of things that we've been discussing. And we tested this controller in space, actually, and this is one of the coolest results. We've tested that in space. To the left is the sun vector. So in black and gray is before we activated the controller, and in red, the squares in red show the sun vector converging like sort of this bowl towards this circle, which is some form of tolerance. And then to the right is the angular momentum measurements, angular velocity, sorry. And you can notice that both omega x and omega y they go to 0, while omega z goes up, which is one of the principal axes of inertia. So you can see that all those things happening real time. And hopping a little bit on the concept of Pi4 information fly and satellite swarms, it's something pretty interesting to enable cooperative space autonomy. It's currently unavailable for magnetorquers. It was one of the things we wanted to try there, but fortunately the mission ended before that. There were multiple high-level tasks that you can do with information flying. So a few examples include astronomy or wildlife tracking. There are a lot of things with collaboration between satellites that can be done, and that would open a lot of scope. And differential drag is a very effective method to achieve that. So Planet, for example, has done a long track separation formations with that. So just here, it's a long track just means in this orbit, just in the same direction of the orbit. And this differential drag is just you have two configurations of the satellite. One of them is high drag, so you have a lot of surface area. It's very related to the surface area. So you're just using that as an aero brake, and then you can modulate that to achieve formations. Now, the main issue is current actuation is too large and too bulky. So a reaction wheel is $5,000 and it's decently big. You can get like ion thrusters, which are $50,000 and even bigger. And I mean, you can see there from like, they're about this size. I'm not sure how those things would fit inside of this. So it has been shown that like in those cases, like achieving some formation flying is achievable with a fully actuated satellite. So previous research by other members of the lab have shown, for example, you can do a box formation and of the satellites, and you can get, so think of it like a long track is one plane, a cross track is just like you're moving that plane like that. But again, this is assuming you have actuation and you can generate torque in all three directions. But we can do that with magnetorquers. And that jumps back to the Lyapunov controller that we were showing previously, where instead of showing an inertially fixed reference, you follow nadir pointing. So you're just trying to point that angular momentum vector to the center of the Earth. So and then you just switch between a major spin, a flat spin. So you just think you alternate between a hot dog and a burger spin. And by that, you can achieve different levels of drag. And it's a very similar flavor to what was shown before. The only main thing is here you got a reference that's as of t, so which is essentially a normalized direction of your velocity. And We've tested that in a very similar setting to the previous section with 100 Monte Carlo simulations with a high aspect ratio satellite with an aspect ratio of 36 between least area and most area in very similar orbit. Though the thing here, because you're trying to rotate and the torques are very small, you have to spin very slow. So the goal of 3 degrees a second is a little bit slower and a little bit more unstable, but it's still doable. And an important thing to show is like here's major axis and minor axes. The RMS of those two is about 15 degrees, but in that case, the cosine of 15 degrees is 0.97. So this is almost the same as perfect nadir pointing. So it more than does the job of achieving that drag ratio. Now, we integrate that with a high-level planner, with an MPC planner that was developed in the previous work from other members of the lab that was done before. So you can essentially, over one orbit, depending on which mode of spinning you are, you can just assume an average of that throughout the whole orbit. And so you can reason over this with the MPC and then use the Lyapunov controller as a low-level controller. And we have done the same sort of experiment with using the drag ratio that we achieved from that experiment, which was around 3 to 1. And we were able to achieve cross-track separation. So we were able to achieve this shifting of planes that I was talking about earlier. Now, of course, compared to the left with a fully actuated system, it doesn't perform nearly as good, right? Here's like a lot more of separation, of cross-track separation. So 0.6 degrees compared to 0.3 takes a lot longer, though the fact that it's still achievable is something that changes a lot of paradigm for those small satellites. So in conclusion, those controllers, they enable a lot of, you can do a lot even though you're under actuated, and in resource constrained spacecraft, especially where, it would just at the best try to detumble and hope that it lasts as long as you can actually get something spin stabilized. You have some guarantees of pointing your satellite to the sun. And that's something that we have verified on orbit. And it's something that we also aim to do with differential drag with future missions. Now, let's jump a little bit into the next contribution, which was the lack of resource-only navigation with visual-inertial navigation. Those were the publications related to that: Lost in Space, InSat, and Lunar Voodoo, published in ICRA and Space Computing Conference. So this starts with a lot of those small satellites and CubeSats, for like this one, this VRAX, and the one was homegrown in the lab. A lot of them get lost or not identified after launch. So if you're doing formations and a lot of that stuff, radio ranging is simply just not good enough to distinguish between them. So even in some cases, you get, for example, in the red line, you can get like 20%, 1/5 of your satellites are not identifiable or lost. And that's a huge deal of them. They're just, getting built and launched without pretty much almost dead on arrival for a bunch of those purposes. And the current methods, so radio ranging is, too slow. It takes a very long time to do orbit generation. We'll go a bit more over that. Satellite is also not suitable. I mean, you cannot fit a commercial space grade satellite receiver, a GPS receiver in this tiny little guy. And this is one such example, like this Novotel receiver. It was in the 5-4 mission. It was $5,000 and the single most expensive component in the spacecraft. And just for here, real life comparison of size, I mean, it's laid down, but it's one board that you're losing that it could be using for payload or for computer for other purposes that is just going to a GPS receiver. At ground radar is, as I mentioned before, it's very slow. You need a lot of measurements over time. So you just have one direction, and it's just distance. So you have to, it's necessary to have a huge deal of them over large amounts of time, like at least weeks to months, to get a good lock on your satellite. So especially given those missions, they don't last very long, this is especially detrimental to how much you can do with your satellite. So how to find a satellite's position with no external input. So that's called the lost in space problem. So how can a spacecraft figure out where it is with no external input? And visual inertial navigation is one of the ideal substitutes, right? We have all this stuff we talked about previously, good cameras, good compute. So why don't we point a camera down and see what we can achieve with that? It's very cheap compared to, I mean, even with the GPU and a camera, it can cost less than $100. It's super compact, lightweight, and it's very high accuracy. So compared to other methods. So let's dive a little into how this works. So think of it here, cool little satellite here in this case, going around the moon. You don't know where you are, like every camera pointed down. You're like, okay, I'm around this region of the moon. Cool, that already gives them some information about it. Now, within the region, these are those small little details on this image that show me, okay, I'm flying above those landmarks. Then this enables to calculate some vectors, unit vectors to those landmarks, which in turn enables the satellite to understand its location. And this is the visual navigation pipeline that we've come up with. We've separated it in two parts, in vision and state estimation. So let's go a little bit more into the vision pipeline. So we had two application cases, one terrestrial and one for lunar orbit determination. We generated data sets in-house with publicly available imagery. One was mosaics with Landsat and Sentinel images for the Earth, and we used lunar reconnaissance orbiter images on the moon and rendered it in a Blender environment. And the landmark selection just came from saliency analysis. So you just run us through the image and go like, okay, what are the features that stand out the most? We did that both for the moon and the Earth. So in this case, everything that's shaded like bright white are salient regions of the Earth, which interestingly are mostly coastal regions with very little rain. And just going a little bit more detail, like about how this works, thing like this blue line is an orbit, a piece of an orbit flying over the regions of interest, which are shaded in green. Then let's say we grab an image in that moment, flying over that red circle. And then from there, like machine learning, object detection. So first image classification, like, okay, we are flying over this region of interest. Then within the region of interest, there's a different model that predicts certain features, which are objects in that case. And here's also a video of tumbling. I'm not sure how good people can see this. People can see the red dots as the satellite tumbling, just showing the landmarks as the satellite tumbling in the simulated environment. So, okay, cool. We figured out, okay, we can identify stuff that we're flying over. So what do we do with it? So here we've solved this as a constrained nonlinear program. So we're trying to minimize our measurement error subject to dynamics. And we're just essentially trying to find a set of solid states. So position, velocity, attitude, and angular velocity of the satellite that minimize that error. And that measurement error, we've tested in different shapes and forms. So I've done PNP, position and point measurements. So that gives you position and attitude. So just a time series of positions, essentially, and attitudes. And camera reprojection. So we compare pixel to pixel of that state. So we have an estimated state and compare what those features in the camera look like from your measurements compared to what your estimated state is. And then we'd use dynamics as a constraint. So orbital dynamics, attitude dynamics, those things are very well known. So this is super helpful in generating, you're essentially fitting an orbit to all of that. And in that context, in terrestrial simulations, we achieved over 80% success rate of less than 5 kilometers error within a time span of 6 hours, which is pretty good considering for a lot of, for example, for one of these, it took a week at least for when we were flying another one of those to locate in. And, we can do that within 6 hours. That's amazing. And in the lunar case, which is more benign, over a very extended period of time, actually can get to hundreds of meters of accuracy, which is comparable to what the LRO achieved in months, getting ranging measurements from the Earth. So now any satellite with this system, any satellite, you can plug it in and toss it around the moon, will be able to locate itself within a few hours. So to conclude, it is a viable method to ground-based methods and GPS. There's a little nugget there, which is we trained the model on synthetic lunar imagery as well. So just making a render of the moon and then tested it on real images. So there was this sim to real gap that was bridged. It was pretty cool. And then also the accuracy and time for OD is far outperforming any of the other methods compared to how much we're putting in it. We try to do some of that embedded machine learning for vision in one of the missions that we've flown. There's a picture to the left. I mean, it says water. It took a picture. You see, it's pretty much black. It said water. Didn't work that well. But the mere fact that we could run that, it's pretty interesting. But we'll try again. There are some other things brewing, and those are the. And now we're gonna get a little more into those two projects. So yeah, we're gonna bridge the barrier to entry for hardware and software, and some of the open source hardware and software that was developed here. So these are some of the publications related to that, with thermal management considerations for microrovers, not covering that much of it in this presentation. You can read the thesis proposal document if you have more interest. And then there's the Pi-4 and Prometheus 1 missions. Now, the satellites, they present an enormous barrier to entry, as we were discussing in the introduction. So satellites, they require everything to be custom made. Cost is extremely high, millions of dollars. So like, how can a university or any other research institution get access to that? And there's not a lot of things that are open source, for people to just grab like, oh, let me get a GitHub, copy everything, launch it into space, and it will work. And this is where I've been showing this guy a lot this presentation, but that's where the pocket cubes and small satellites come into play. So this is the topic that we're gonna address. So Argus and Prometheus are the two projects for a CubeSat and a pocket cube that developed during my work here that will fill that gap. So Prometheus is super simple and modular. It's essentially 11 PCBs just bolted together that you can throw into space, and it will actually survive space and send stuff back to you. And it's also based on CircuitPython and the PyCube platform. So anyone who knows Python a little bit can just code stuff to put in there and try to, if have some really cool algorithm, like, hey, I did this cool algorithm. What if I just try to launch it into space? You can just do it in Python and toss it in there. And PyCube has it's an open source platform discussed before. It was on Pi-4. It was here on VREX. There's plenty of flight heritage into it. And for its tiny size, it has big autonomy. So there are two MCUs, number 5 and number 2. So there's one dedicated, kind of like the reptile brain of the satellite. So it does the more low-level stuff, like pointing and stuff like that. And then there's a second one, which is it's a more robust processor that's devoted specifically for computer vision and machine learning tasks, and that's in the camera board. So as a camera board, it's impressive what you can do with those cameras these days. So it's pretty interesting. And all of that is also bolted to very easy and accessible radio frequency communication. So it uses LoRa modules. So it's literally the same thing people use to open their garage doors. It's something that we have installed in a ground station in Portugal with an egg beater antenna and a Raspberry Pi. So if you have a Raspberry Pi, a soldering iron, and a few cables, you can actually communicate to your satellite in space. So all that, as mentioned many times before, has been operated in space. To the left is a picture of Prometheus being deployed this February, and to the right is integrated into the pod for deployment. And it actually worked in space. We managed to get telemetry packets and that image that I showed before. There were a few things that happened. For example, it was biased more towards the cold, so -6 Celsius, a little bit chilly, which is to be expected. Now, the intriguing thing is the gyroscope measurements were showing an extremely fast tumble rate of essentially 2 revolutions per second. So that's one of the probable reasons why there was like those like features here in this image, probably the stars that are getting streaks. Even though all the happening results are very encouraging. I mean, one of those pocket cubes cost $500 to make. So we can launch much more of them, and we're very excited to send another one to space. And another thing that we're really excited to send to space is Argus. So it's also another satellite project that's being developed here. It will deploy the visual-inertial navigation that was shown before. It has a lot of the cool things for robotics that I was talking about before. It has a Jetson inside, so it's capable of doing very complex machine learning tasks. It's somewhat based on the PyCube platform, so it has flight heritage, it's robust, and it uses all those like new cameras that are fairly accessible for for $50. You can get a 4K camera, and now we're integrating all of that into one satellite. So to conclude, we have a flight-proven pocket cube that showed real-time onboard autonomy, even though we classify space image as water. It's still remarkable that we could run an inference model in space. And low-power machine learning and computer vision were executed under extreme hardware constraints. And I mean, just for reference, the weights of the network that we ran for this classification was 300-ish kilobytes. So it's extremely lean, and it's just remarkable that that could run. And this is all super modular, so other people, it's available on GitHub. Anyone who wants to try and make their own Pocket Cube can just open the GitHub, get all the documentation, change it as they will, and integrate that. And that's just very exciting for research, education, and some repeatable experimentation. So people can just, like I said, spend $500, find someone to give the other 15,000 to launch it, and then launch it into space. Now, we're jumping a little bit into the reliance on ground infrastructure. So we're going to talk more about onboard georectification. And just for context, we're working with Planet Labs with this. And the problem we're presented is performing onboard geolocation and orthorectification in their Pelican satellites. So let's say you have this super nice high resolution 4K image of a port. So how can we pinpoint where that ship is? How can we pinpoint where those warehouses are? And this is something that we need to run in the satellite. So all this stuff now is done on the ground, and it requires a lot of computation and a lot of resource. And even worse, you cannot really choose where you're running all that stuff, where you're localizing stuff. There's a lot of like ground and human in the loop type stuff happening. So how can we make that autonomous? And the really interesting nugget here is that it's very closely related to the lost in space problem. It's essentially a forward problem of that, right? So in the lost in space problem, you know where things are on the ground, but you don't know where the satellite is. But now the problem we're trying to solve is the forward version. So we know where the satellite is. How can we know exactly where things are on the ground? And the planet is a unique opportunity for that because it's something that we can try on orbit. They have hundreds of satellites on orbit right now and planning to do stuff, really smart stuff on orbit. So it's a very unique experience to be able to design something and then integrate it into a satellite and fly it. And by the end of it, hopefully have some orbit results. So there are a few objectives that are coming from this proposed work that's going to be done the next year. So first of all, devise an algorithm for an orbit georectification. So what are the algorithmic steps? How can we adapt all of those methods that were done for lost in space? So the batch estimator, the computer vision algorithms, how we can fuse all of that in a way that we can achieve less than 1 meter per pixel rectification error. And that's something that's going to be done between now and August. Then the next step is like, cool, we got something that can do this very, very nicely with a lot of accuracy, but how can we do that with all of those resource constraints? So how can we run all of that on orbit? So, trying to optimize all of the computer vision data. So like, how can we say, these are the landmarks you need to be looking for? Like what with a task, like, oh, we need to locate stuff here. Like, how can we minimize the bandwidth of uplink that is related to that, or energy as well? So like, how can we run all of that, like being able to then with all of the requirements that pertain to power budget and duty cycle and memory and compute, all that stuff. And this is something that will be done between June and November, so a little bit concurrently with the designing of the algorithms. And then finally deploy that on orbit, put that on a satellite, collect a bunch of data and see like, okay, did that actually work? And that's something that'll happen between November and February. So is that something that worked? So in a timeline for graduation, there are a few things that, and defending, there are a few things that need to be done. So first of all, in ISPRO, there are 3 publications in the queue now. So 2 of them, the magnetorquer stuff that I've talked about in this presentation, submitting that to ISPRO, the International Space Robotics. Then one of the algorithm papers from the first objective. So we've developed the algorithm, get that published, and towards March 2026, try to publish the results from on-orbit testing with some on IROS, which will then lead to a defense in April. And with that, I thank everyone for your presence, and I'm open the floor for questions. Thank you. For
the general scale of satellites in space. So